Now we attack a formal mathematical part of our discussion. When Lagrange did this, he was elder, 24 years old. Okay? So let us consider a system, the model of which is finite dimensional. So you have n degrees of freedom. Q1, Q2, Qn. I will not dare to change the notation of Lagrange. He calls them Q1, Q2, Qn, and we call them as Lagrange code. The whole collection of these n parameters we will call Q if we need. Okay? So every configuration of our system is characterized by these n real variables. What can be the system for which we are introducing a mathematical model? Whatsoever can we generate? So in a sense, we are developing the theory of every mathematical model finite dimension. This is suggestive. This is very exciting. We are introducing the theory of every mathematical model. We are talking about Lagrangian mechanicist way of considering the world, the universe. You know, the reasoning, we will come back to this, the reasoning of these people was the following. There is a finite number of atoms in the universe, and it can be very large, but it is finite dimensional. So, with the reasoning we are going to develop, in principle, we can write the equation of evolution of the universe. So, in a sense, this was the theory of everything. This is the dream of writing the equation governing the evolution of everything. This is a dream. Okay? So, following Lagrange, we introduce a function. Back to why this function is capital L. The Lagrangian function, which is a function of Q, Q dot, and T. We keep that door closed. Okay? Now, I must tell you what is Q dot. We can talk about a motion in this system. The motion is a function which, to every instant t, associates a configuration Q of t. So you think always to the examples I gave you. Material particle, rigid body. So, a motion of a material particle is a function which, to every instant t, is giving to you the position of the material particle. The motion of a rigid body is a function which, to every instant t, gives you the position of the bicenter and the orientation of the three vectors which are solid to the body. Think about the Lagrangian system of world economy the configuration of this system is given by Q1, the national gross product of United States, Q2, the same of China, and so on up to Qn, the last national product of the smallest country. Then you have P1, the value of $1, P2, the value of €1, and so on, Pn. And you can keep introducing parameters, trying to shoot a picture characterizing the state of the world economy. What is the motion in this case? Is the function, which in every instant gives you the value of all currencies, the national gross product of every country, the number of unemployment in every country, and so on. I tell you that this is also a Lagrangian system. So you should not think that we are talking about only mechanical systems. Okay? So you must think general. You have a system. You don't need to ask you which one. It is a system. You know, in Greek, physike means what is existing in nature. So physics, in the sense of Greek language, means everything which we are observing. So you have a generic physical system in the Greek sense. And you have a mathematical model describing the state of the system. This mathematical model is characterized by n Lagrangian parameters. So when you know the value of these n Lagrangian parameters, your model tells you which is the state of the system. A motion is a function which every instant t gives you the configuration of the system. Can we derive with respect to time these functions? Yes. So Lagrangian velocity is the derivative with respect to time of the function q of t. And you get another function, the q over dt, which we can also call q dot, or doing it short. Okay? So, our system in a motion, you shoot a picture in a given instant, and you know its configuration and its Lagrangian velocity. Okay? So you know q and q dot. Now, Lagrange function is a function which, to every configuration, to every Lagrange velocity, and to every instant, associates for you one real number. So this is a real number. Okay? There is nothing strange in what you have. You have a function. This is a rule. Give me the configuration, the Lagrange velocity, and the instant t, and using this Lagrangian function, you can calculate a real number. There is nothing strange. Okay? Now, you can can define a function. I give you a motion, okay? Q. I have used the dot in the center of the two brackets for meaning that I don't consider one configuration, but I consider the whole function motion. Then what I do? I consider the Lagrangian at the calculated in Q tau. Tau is a parameter for time. Q dot tau, tau. What I get? This is the composition of the function L in terms of the function Q dot. Okay? As a final result, I get a function of tau. Then I consider my motion. My motion starts at instant t0 and ends at instant t final. And I calculate the integral between t0 and tf of L of q tau, q dot tau, tau, d. So I'm giving you the algorithmic instructions for building, starting from the motion, a number. I call this number the action associated to the motion Q. So the action is a function. Okay? To every motion, the action is associated a real number. Okay. Now, an American historian of science claims that the first statement of the principle of minimum or least action can be found in a textbook of an ancient South Italian Greek philosopher, Archytas of Tarentum. We claim the following: nature is always minimizing action. The nature chooses always a motion which makes this functional minimum. Look, this is a conjecture. The question how you prove this is meaningless. Okay? I can tell you that every mathematical model can be suitably reformulated in order to be the minimum of a suitable action. This is true for sure. Okay? However, somebody can tell you that people are using different principles for getting equations. I don't believe so. I don't believe this. I believe that everybody is doing like people in continuum mechanics. Piola proved the validity of some equations starting from a principle of minimum energy or minimum of action, the original deduction has been lost, and people rediscovered after some time the variational formulation of the theory. But of course, this second statement can be debated, so we will not lose time discussing that. I can give you books if you want to study this point. Okay. But what is important is that this principle is producing you the equation of motion of every mathematical model available. So, we know what? We are very good now in calculating the first variation of functions. We have already done it 2 times. So, we do it a 3rd time. So, I don't know if you are understanding. I'm trying to hammer in your head variational principles and the calculation of the first variation of a function. Okay? So, what we do? We consider a motion. You start from Q0, T0, and you arrive to Q1, T1. You have an initial configuration and a final configuration. The initial configuration you have at instant T0. The final configuration you have an instant T1. Okay? Then you consider the motion Q. This motion verifies the conditions that Q at instant T0 is equal to Q0 and Q at instant T1 is equal to Q1. So you have a motion which is starting from a configuration in a given instant and is arriving to another configuration in another instant. Okay? Then you consider another motion which is obtained with a small variation of the first one. So you have this other motion. However, the second motion is isochronous, which means, in Greek, having the same time. What it means? Q of T0 plus delta Q of T0 equal Q0. At the instant T0, this motion starts from the same configuration. As Q_T0 is equal to Q0, isochronicity, the fact that the two motions are isochronous, implies delta Q_T0 equal 0. Okay? You have understood that Q0 is Q01, Q02, Q0n is a vector. Okay? Delta Q is also a vector. And again, delta Q T1 is equal to 0. So, admissible variations of the motion verify these conditions at instant t0 and instant t1. Okay? So again, we must feel very small, very stupid, because Lagrange was developing this idea when he was 24, 25. By the way, he got a full professorship in Berlin, being, I think, 29. Then he spent 40 years in Berlin, and then he moved to Paris, where he spent another 20 years. Okay, so we need to look for the minimum of action among the set of motions which are starting from Q0 at instant t0 and are arriving in Q1 at instant t1. This is beautiful. This is very powerful, because computers are like very much to calculate the minimum of something. We have very powerful algorithms for finding the minimum of something. Okay? So if we base our theories on a minimum principle, this theory is automatically computable. Okay? So you can use the theory I tried to start teaching you in a very efficient way, and you can forecast the motion of a system. So you can say what will happen. Okay? So all these painful calculations are aimed to learn how to forecast the behavior of systems, physical systems. Now, I must tell you that mechanics is very powerful. You can send a device which leaves Earth and arrives on Mars with an error of few meters. They carefully designed the trajectory, and they needed to adjust it a little bit using electromagnetic signals. Okay? On the other side, there are parts of human knowledge which are not very well known. Economy needs to be developed because we still need the correct equations for describing the evolution of the economical system. For instance, Angela Merkel, she is PhD in theoretical physics, was asking to her experts in economy, what happens if Greece will declare default? After 3 hours, they told her, we do not know. So she decided not to allow to Greece to declare default, because the consequences could be dramatic. Okay? Why? Because nobody has already invented the Lagrangian, which is able to describe the economical dynamics in the world, which has to be found. Okay? So you have to understand that there are models which are very good, very effective, models which are not ready yet to drive our decisions. Okay? Good. Now we stop talking and we start calculations. I am tired. I'm not writing the brackets. These are functionals. Okay? So as we have done this already 2 times, I will jump some passages. But if you have some doubts, you stop me. So this is equal to integral of what? Lagrangian in Q plus delta Q, comma, Q dot plus delta Q dot, comma, tau, minus Lagrangian of Q, Q dot, tau. Delta. Okay? Simply because the integral of the difference is equal to the difference of the integrals. Okay? Now, next step. Next step is the following. I have a function, the Lagrangian function, and I have the increment of this function. So I can use Taylor expansion for approximating this endpoint. So you see, the ingredients are always the same. You have L of Q plus delta Q. Q dot plus delta Q dot minus L of Q, Q dot. So, alpha action of Q plus delta Q minus action of Q is equal to the integral between T0 and Tf. Okay. Now, maybe you remember, I got right dl over dq1, and here I must write the increment of the first value, which is delta q1. Okay? Then I have dl over dq2 delta q2 plus delta l qn delta qn. Is it ended? No, because I have the variation of q dot. So this is plus delta dl over dq dot 1 delta q dot 1 plus dl over dq dot n delta q dot n. Okay? Plus infinitesimals. So we have the remaining. Okay. Now, when we neglect the infinitesimals, the finite increment becomes the first variation. So delta action is not the increment. It is the linear part of the increment. Okay? Look, I remember exactly. I had your age when I learned this, so you can do it. Okay? So, when you have an expansion, the finite increment includes the remainder. If you forget about the remainder, the increment becomes the first variation. The first variation is a linear function of the variation of the independent variable. So when you kill the infinitesimals, you get the first variation. This is integral t0, t1 of dl over dqi delta qi, sum over repeated indices, plus dl over dq dot I delta q dot I. Okay? This delta A has to be 0 for every delta Q such that delta QT0 is equal to 0 and delta QT1 is equal to 0. So this is very similar to all the calculations we have done up to now. Okay? And we have the same problem as yesterday. This delta Q and this delta Q are not independent. If delta Q is arbitrary, this delta Q dot depends on the delta Q which you have chosen. So in order to proceed in this deduction, we need to integrate by parts. This I know. Let's go. So, the derivative with respect to time of dl over dq dot I delta qi you must stop and think slowly what we are doing. You have a Lagrangian, okay? This Lagrangian is a function of q dot, and time. You have your motion. Your motion is the minimum of action, okay? Then you change a little bit your motion and you try to calculate the first variation of action. Okay? So, dl over dq dot is a function of q dot, and t. Here, you consider the motion which is minimizing action. So, this is a function of time. And you have delta qi, which is the small variation of this motion. Okay? This derivative you calculate using Leibniz rule. So this derivative is equal to d over dt of dl over dqi delta qi plus dl over dq dot I delta qi dot. We have already spoken about what happens to the small variation if I have a derivative, and we already accepted that there is a commutation of these two operations. The derivative of the variation is equal to the variation of the derivative. Okay? So now, up in the formula at the top, we have this animal, and this animal is equal this minus that. Okay? So here, we can write plus d over dt of dl over dq dot I delta qi minus d over dt dl over dqi delta qi. So I have simply replaced the result of the integration by parts process. Okay? Okay. Now, the integral of the derivative of sum. We have already met this. The integral of the derivative of sum. The integral of the derivative of something is equal to something calculated at this at the extrema of integration. Okay? So I write here integral between t0, t1 of the derivative with respect to time of dl over dq dot I delta qi. This is equal to dl over dq dot I delta qi calculated t0 t1. Okay? You agree? I don't remember. Somebody told me that you have not the habit of asking questions. Ask. Okay? Don't worry. If I have to go slowly, I will go slowly, otherwise it is useless. You know. Do you know how much is this quantity? Delta qt0 is 0. Delta qt1 is 0. So this quantity is equal to 0. Okay? Therefore, this animal here is not existing. It's vanishing. So I can rewrite the first variation in this way. Okay? Now, delta Qi can be factorized on the right. We are very close to our result. Okay. If we consider the action function built with a Lagrange function, this formula you have on the blackboard is the Taylor expansion truncated at the first stop. Indeed, look, this is clearly linear in the variation of the motion. Okay? So this is the best possible approximation of the variation of the action in the set of linear functionals. Okay? Now, we have done it already 2 times. Minimum, maximum, or if you like, stationarity condition is equivalent to impose that this quantity is equal to 0 for every delta Q. Okay? Now, I want to underline how powerful this element is. Because how many independent variations you can have for delta Q? How many components you have in delta Q? You have exactly n components. Do you remember? The configuration is given by n parameters. The motion is given by n functions, and you have exactly n independent variations. What we will discover is that we will get exactly n equations. The power of variational principles is that they give you always exactly the number of equations which you need. Not one more, not one less. So what you can do, you can choose delta Q 2, 3, 4, n equals 0. And you choose in an arbitrary way delta Q 1. So delta A equals 0 for every delta Q implies that this equality is verified where delta Q1 is arbitrary. Okay? So again, we can reproduce the reasoning we have done yesterday with the function doing this job. This time we will consider a given instant t in your interval, and what you get this equation. Of course, you can repeat this for Q1, Q2, Qn. So, for every I, you have this. Do you know how we are called these equations? These are the celebrated Lagrange equations. These are ordinary differential equations. We will see how we understand this. So we have to be slow, because you may believe that these are pieces of chalk on a blackboard. Indeed, they are pieces of chalk, but they have a meaning. For a long while, mathematicians believed that these are the equations of everything. These are the equations of the universe, the equations of every system. Give me a Lagrangian. A Lagrangian is a function of qi and q dot. Calculate this partial derivative. Calculate this other partial derivative. Then you calculate this time derivative, you get the equation of motion. Consider a system with 1 degree of freedom. We call it X. Okay? And consider this Lagrangian. Don't ask me how Hamilton had this idea. Okay? Consider this Lagrangian. So, I is equal 1. Okay? dl over dx is equal to kx minus okay dl over dx dot is equal to mx dot. D over dt of dl over dx dot is equal to mx double dot. Now I write the Lagrange equation minus kx minus mx double dot equal 0. Do you recognize it? This is the equation of a mass with a spring. Okay. This is a simple example which is good enough for us. Why? Do you remember how complicated was all the story used in the course of physics to persuade you that this equation is good? They said, you have inertia. The force is producing acceleration. The mass is the coefficient linking the force to the acceleration. So, do the list. Look, if you are here in the warmth of this room, hearing somebody speaking a Neapolitan English, okay? You must earn something. Okay, otherwise it is useless, all these efforts. So, do the list of painful assumptions which you needed to accept without any explanation. The force of inertia is proportional to the acceleration. Why? Believe me. The force, external force, is equal to the mass times the acceleration. Believe me. The force applied by a spring on a mass is minus a coefficient times the displacement. Believe me. Then I write this equation. Believe me. Okay? This is good, this equation. I can even believe people telling me all these things. But we needed to believe too many things. Okay? So what is wrong if I tell you, believe me, this is the Lagrange? Where is the difference? I tell you, where is the difference? You accept only one thing. The Lagrange is this one. Period. I tell you more. A force is a vector. The acceleration is a vector. The Lagrange is a scalar. It's a number. Much easier to handle a scalar quantity than a vector quantity. Lagrange point of view is the following. Do you want to model the behavior of a mechanical system and its interaction with the external world? Find the Lagrange. Do you want to model the interaction of the Sun with all the planets? Calculate the kinetic energy of all planets and subtract the potential energy, the gravitational potential energy of the interaction between every pair of planets. This is the Lagrangian of the system. Okay? So, I strongly suspect that every mathematical model has been invented using a variational principle. I strongly suspect that people are frightened by the calculation of the first variation of an action, because you need to learn a lot of technical details. So how people are behaving, they read the final result, and then they have visions. External force is equal to mass times acceleration. The force is given like this. So what they do? They look at Lagrange equations and then they delude themselves. They persuade themselves they can find a physical reasoning for getting these equations. Okay? Now, when I was a young PhD student, my professor said, your PhD thesis is phase transition. You must study how a drop of a liquid is evaporating under the action of external pressure. I tried to have a vision and find the correct equations. I did not manage. I could not have the right vision. How did I find the correct equations? When I met the poor late Witold Kosinski, who was professor at IPPT Bank, when I met him, and he told me, try with this Lagrange. In my opinion, this is one of the most powerful tools which we have for inventing new models. And you must recognize equations which you already found. Okay? So, for instance, if you have the vector x with components x1, x2, and x3, and you have the Lagrangian L 1/2 mx dot squared. This is the length, the square of the length of the velocity vector minus u of x. Where u is a suitable function of x. Okay? Then find u for having the motion of one planet. So you should look for the potential for the motion of one planet. Okay? Then consider x1, only one degree of freedom, and the Lagrangian will be e to the minus t over t0 times 1/2 mx1 dot squared minus k x1 squared over 2. With this Lagrangian, this is the exponential, never number. Okay? With this Lagrangian, you will discover that it is not true that only conservative systems are Lagrangians. Because this should give you the equation of the motion of a mass under the action of a spring and linear dissipation. Okay? Then consider two particles. So, two material particles. The first X, so X1, X2, and X3. The second Y, Y1, Y2, Y3. Okay? Write kinetic energy T equal 1/2 m1x dot square plus 1/2 m2y dot square. And then, as a potential energy, you assume K over 2x minus y squared. I think that this is enough for practicing with these ideas. Okay? Okay. Now, I want, as we have changed our plans, we can use a little bit more time. So I can tell you next complete part of our course. We can study a little bit the structure of Lagrange equations. Okay. What is beautiful is that Lagrange equations can be solved. So you can find a unique solution with an algorithm. So there exists a constructive way for building a sequence of functions which are converging to the solution. This theorem, which has been proven by Cauchy exploiting an idea of Bursa, has been then generalized by Cacciopoli and by Banach in a very general setting. Okay, so in my opinion, this is a technique which is both very important from the conceptual point of view and very useful from the practical point of view. Because using these results, you can build a solution. Of course, you don't get the solution in an analytical exact form. You build a sequence of functions, and this sequence of functions is converging to the solution. So let us see in more detail this. Okay, so we investigate a little bit minus d over dt, dl over dq dot I plus dl over dqi equal 0. These are Lagrange equations which we have found. L is a function of Q1, Qn q dot 1, q dot n. Okay? I gave you some examples. Okay? So you see that dl over dq dot I is another function of all these variables. Okay? So if I ask you to calculate the total derivative with respect to time of this function, where here you have the solution. So you have q1 of t, q2, qn of t, q dot 1 of t, q dot n of t. You can calculate this derivative using the rule of compositions of derivatives better. The chain rule, the derivative of composite functions. Okay? So, what you get? You get the derivative of L with respect to q dot I derived 2 times with respect to qh, q dot h, sum over h. Okay? Minus the second derivative q double dot h, okay, minus plus dl over dqi. I see your faces worried, so I give you an example. Okay? Assume that you have a function f of x, y, and z. Okay? Then you have f of x of t, y of t, zeta of t. Then you must calculate the derivative with respect to time of this composite function. Okay? How you calculate this? df over dx, x dot, plus df over dy, y dot, plus df over d zeta, zeta. You agree with this? Okay. Now, here we have a function dl over dq dot. This is a function of qh. So I consider the composite functions qh of t, and when I calculate this derivative with respect to time, I must calculate dl over dq dot d over dqh times q dot h, as I've done there. Okay? But dl over dq dot I is also a function of q dot h. So I must calculate this derivative times the derivative of q dot, which is q double dot. Okay? This element remains unchanged. Okay?
Wiecie, czy nie? Coś jakoś tak chyba tu nie za bardzo. Co pan po?
Sure?
Tak.
Okay. Now, you know that there is a beautiful theorem due to Schwarz. So the order of partial derivatives is not important. So I can write second derivative of dq dot I dqh, and it is the same stuff as before. Okay? Now, why I wanted to do this derivative? Because if you call capital A H K H I the matrix of second derivatives of the Lagrangian with respect to Q dot H Q dot I. This is what is called the Hessian matrix of the function L. You have that this matrix applied to Q double dot H plus this other matrix applied to Q dot H, okay, minus dl over dqi is equal to 0. Now, a well-behaving Lagrangian has a peculiar property, as remarked by Legendre. This matrix must be non-singular, so you can calculate its inverse. Okay? If you can calculate the inverse of this matrix, then you multiply times the inverse of A, and what you get? You get Q double dot H equal something on the right side. I don't want to write it explicitly, but this something is a function of Q and Q dot. I told you yesterday that Napoleon considered very much mathematicians. Okay, so also Napoleon III, the nephew of Napoleon I, pretended to have a high consideration of mathematicians. So he invited Laplace, and Laplace gave a talk in front of the emperor, and he spoke about these equations and said, these are the equations of everything. Give me a system whatsoever. I find for you the Lagrangian, and I can integrate these equations for you, and you will know what will happen to this system in every future instant. Okay? Then Napoleon III was not so clever as Napoleon I, and said, Monsieur Lagrange, what about God? And Laplace answered without moving a muscle. He said, this is an hypothesis which I don't need in my model. Okay? I tell you this for underlining how important has been this equation in history of science. For a long while, mathematicians believed that they could forecast everything using this. This philosophy is called illuministic mechanicism. Okay? Quantum mechanics has destroyed a lot this belief. Okay? Now, imagine how important is the problem to find a solution of this equation. If you believe that in your hands you have the equations of everything, and you must be sure that you know the solution, otherwise you are lost. Okay? So, we call ordinary differential equation or system of ordinary differential equation, a system of equations, they are called ODE, ordinary differential equations in English. ODEs. A system of equations in which on the left hand side you have the derivative of higher order, and on the right side all derivatives of lower order. Okay? So you have a system of equations in which the knowledge of the configuration and the knowledge of the velocity, Lagrangian velocity, in a given point, in a given instant, gives you the higher order derivative. So if in a given instant you know where you are and how quickly you are going somewhere, then you know your acceleration. Okay? Now we do a game, a mathematical game for simplifying the equation. It is a formal game. By the way, this formal game is due to a man whose name is Hamilton. You know, it is very strange. Variational principles were born in Taranto, most likely. Then they moved somewhere in Arabic countries. Then they moved back to Italy. Then they went to France. Okay? For a reason, after the continuator of Lagrange was a British scientist. Hamilton. So it is not true that variational principles are continental and balance equations are British or Anglo-Saxon. Because one of the biggest and deepest scientists using variational principle was Hamilton. Of course, other British people despise him very much. You know, you find very controversial opinions about, for instance, Truesdell wrote that Lagrange is a mediocre scientist under the bad influence of D'Alembert. God will forgive Truesdell. Because variational principles are difficult to understand. So people, when don't manage to understand something, declare that they are empty. So if a concept is difficult, instead of admitting I don't understand it, it is much better to say garbage, not very important. Okay? The trick of Hamilton is the following. I call V Q dot. Okay? So this equation becomes V dot equal f of q and v. Okay? And then q dot equal v. Of course, the trick of Hamilton can be changed. There are equivalent forms, but in this moment, we don't mind. Why we don't mind? Because we pay something and we earn something else. What we pay. Before, we have n unknown functions. Now, we have 2n unknown functions. So the unknown functions are q and v. Okay? So we double the number of unknown functions. But we earn a lot. This is a system, a system of ordinary differential equations of the first order. You have only one derivative. And believe me, this is very important to get. Okay? If you know the solution of this system of equations, you obviously know the solution of this solution. Okay? So, this is a trivial theorem, but very important. Every system of ordinary differential equations can be reduced to a system of ordinary differential equations of the first order. Okay? So, instead of considering the second derivative, instead of attacking the study of this equation, we can study another system of equations. P dot equal f of p. Of course, p belongs to Rk, where k is f. Could be 300. Okay? Okay. Now, of course, when I was in Warsaw, everybody was very proud of Banach, Tarski, Copernicus, and this thing. So, I was Italian at the beginning. You know, Italians are not very nationalistic. But recently I'm becoming old, and so I am very happy of telling you that this problem has been studied very carefully by a Neapolitan mathematician whose name was Cacciopoli. Cacciopoli was typically South Italian. He wrote a few papers, and he was meeting people and telling, do you want to write this paper? I give you the idea. And sometimes the person added the name of Cacciopoli among the others, and sometimes he forgot. Okay? However, in the lecture notes of Cacciopoli, they have found the modern demonstration of the existence and uniqueness theorem for the solution of this equation. Okay? And what is amusing, on the tower of a pizzeria in Vomero, a quarter of Naples, it is written, handwritten by Cacciopoli, this theorem. Okay, and this pizzeria text is on the wall. Okay? what is amusing is that this was a philosophical problem. I want to prove that the equations which I have written are good as a model, are suitable to give me in a unique way the evolution of the system. So I want to be sure that with these equations I can forecast the future evolution of my system. So this is a very important issue from the philosophical point of view. However, computers are nowadays working because every evolutionary problem with suitable tricks is transformed into this problem. And for this problem, we have an algorithmic solution. So what was a philosophical problem was immediately transformed into a practical problem. Do you want to design an airplane? You need to solve some 100,000 of equations of this kind. So it is not true that philosophy is useless. We are all descendants of Greek philosophy. You can say that in your blood there is no blood of Greek descendants, which may be true. But via Copernicus, your culture became a Western culture, and so intellectually speaking, you are descendants of Greek philosophy. Okay? Now the trick. I know P0, the initial data for our problem. So I know that at instant T0, the configuration, the enlarged configuration, because P0 includes velocities, okay? The configuration of my system is known, okay? Then what I integral between T0 and T of P dot, this is obviously equal to Pt minus Pt0. And this is equal to integral between T0 and T of f of P tau d tau. Okay? This is a trivial integration of your differential equation. So you can write that for every t, P of t is equal to P0, the initial data, plus the integral between T0 and T of f of P of tau d tau. This is so obvious that it is trivial. I mean, this is a simple rephrasing of what we have written before. Now the clever idea. I conjecture that I can build a sequence of functions. And this sequence of functions I conjecture, can converge to the solution of this problem. So, the first approximation P1 of T is a constant, P0. So I assume that my system, for every instant, has this initial data. Okay? This is a possible element. Then what I do? I place P0 here, and I get P1 here, and I calculate P2. So P2 of T is equal to P0 plus integral So the idea is the following. I place here the nth iterate, and I calculate the n plus 1 iterate. So P n plus 1 function of T is equal to P0 plus integral between T0 and T of f p and tau d. Okay? Now, the hope is the following. If this sequence Pn of t is converging, so if you have a limit function, then the limit for n tending to infinity of this is equal to P0 plus the limit of this. If this limit can enter in the integral, if the f is good behaving and the limit enters under the f sign, then this limit is the solution of your problem. Okay? These technical details in this moment here are useless. But I must tell you the assumptions. You know, not everything is always true. You need to assume something about this f in such a way that this limit exists. Okay? Moreover, I don't know if you never heard about the theorem of the limit, the passage of the limit inside the integral sign. This is another Italian theorem, Beppo-Levi theorem. It is also, another version is Lebesgue theorem. But what we need here is the passage of the limit inside the integral. Okay? But I tell you the results. The assumption and some of the results. But before we are precise, I want to tell you why this iterative system, iterative scheme is so important. You take a command do. You ask to do this many times, and you stop it when, for instance, Pn plus 1 minus Pn, Pn plus 2 minus Pn, Pn plus 100 minus Pn is smaller than your epsilon, the error which you can accept. Okay? So this gives you an algorithm. This algorithm is producing for you a good approximation of the solution P of T of your evolutionary problem. And you have a criterion for stopping it. Okay, the good news is that this theorem is so powerful that you can estimate, you can have an a priori estimate of the error. Before starting calculating, you know a priori how many steps you need for getting your precision. This is a revolutionary theory. All software which we have now is based on this theorem. You reduce everything to this. Now the technical information which you need. F has to be Lipschitz continuous. Now, Tommy is already smiling. I don't know how to write Lipschitz. Okay. I think it was German, not Polish.
No.
Huh?
No Polish.
No. So find the correct spelling. It has to be Lipschitz continuous. But I can tell you in formulas, so we don't know. A function f is Lipschitz continuous when f of p1 minus f of p2 absolute value is or not, because f is a vector. This is smaller or equal to k norm of p1 minus p2. So, given a function f, you must find a constant k such that this upper bound is verified. I give you an exercise. Square root of x is not Lipschitz continuous. If f is C1, so if f has derivatives, first derivatives continuous, Lagrange theorem, Taylor expansion with Lagrange remainder, gives you this upper bound. However, square root of x gives you a continuous function which is not Lipschitz continuous. So you have an important information. The important information is the following. If the f in the ordinary differential equation system is Lipschitz continuous, the integration scheme I am describing to you is convergent. And you can use it for approximating your solution. If the function f is not Lipschitz continuous, you are in troubles. Why? Sometimes the solution is existing, but is not given by the iterative scheme. Sometimes the solution is existing and is given by the iterative system. Sometimes you have more than one solution, and sometimes you have no solution. This result is due to Peano. Another Italian mathematician. This is called Peano phenomenon. He took this very naive and simple differential equation. He wrote x of 0 equals 0, and you are lost. Okay? So another time, you cannot be blind. You believe that you turn a machine and you get a result. So practically it works. Then, for a reason, you fall in a system for which the equations are not Lipschitz, and you can get everything. And if you are stupid enough not to understand, you would say, this is the solution. And maybe it is a function which has nothing to do with your problem. Could be even very far. Okay? I want to tell you, before we end the lectures of today, I want to talk about Semberan friction. This has been an example for which, because of which I've lost a lot of time in the last months, because we wanted to study the behavior of concrete. Okay, so I want to tell you that you should never underestimate the mathematical difficulties. You want to study the concrete. You believe everybody knows what concrete is doing. It's not true. You take a specimen of concrete, you load it with a force, it is deformed. So you can plot length of the concrete, applied force to the concrete. And you plot the graph of this. You get a beautiful straight line. Okay? So you are very happy. You say, wonderful, this is a linear elastic material. Okay? Then somebody tells you that you are building your building in a city, like many cities in Italy, where a strong earthquake is very likely. You know, in this country, when we have an earthquake, we have something dangerous. In 1980, in Avellino, we have lost many thousand persons killed by an earthquake. And in L'Aquila, recently, 300 persons died. Okay? So we need to understand very well how a piece of concrete is behaving under seismic actions. So, I woke up one morning and I said, you know what? I apply a periodic load to this specimen and I see what happens. Okay. This happens. The area inside this is proportional to the dissipation in this loading unloading process. This is not very strange that you have a dissipation. What is very strange is that this plot is strongly nonlinear. How it is possible? You load it in static case, it is linear, you load it at 1 Hertz and it becomes nonlinear. Okay, if you are interested in this, because I don't want to give you the impression that I am a mathematician. I am not a mathematician. I am an applied mathematician. Okay, I try to apply things to true little humor and not a mathematician. I am a physicist. Okay? My master is in physics. Okay? We will talk about this in full detail. Now, what I want to tell you is that you need a force, a dissipation force, which is of several types. Here is the force, and here is the speed, the velocity of something. We will discover later what is this phi. You know what is doing this force? When phi dot is negative, it is a negative quantity. When phi dot is positive, you have a positive quantity. Exercise. Prove that this is not Lipschitz continuous. So, I will show you maybe tomorrow or Monday or Tuesday. Okay? I will show you that in order to understand what happens to a specimen of concrete under cyclic load, you need to solve an equation of this kind. Phi second equal K phi plus sinum phi dot. This is now this is not verifying Lipschitz continuity condition. Okay? It is clear. If you are here, this difference is very small, but the image has a very big difference. So, if you want to study what happens to concrete, you need to know what is a Lipschitz continuous function. This is what I wanted to tell you now. But, of course, we will show you all details of this story. Okay? So, the theorem I was simply formulating for you is a theorem which can be used only under specific hypotheses, like everything. And when you apply it, you must verify that the assumptions are valid. You know how we solved this problem? We use an hyperbolic tangent, which is a function doing this. So we regularized, and we were lucky enough to find the correct slope here for fitting the behavior of concrete. You know, we started doing numerical simulations blindly, and we started getting results. You know, when you take out numbers without any meaning, because the system was jumping this side or this side without any regularity, and we got some crazy results which we could not interpret. Then I said, stop it, what we are doing. Okay? In books used in the engineering school of Rome, they solved this equation with some tricks without telling you what they are doing and why they are doing it. So we followed blindly the solution given to us. Okay? Never, you must never follow the recipes which they are giving you without understanding what you are doing. Never. Your roof will fall down and your computer will give you random numbers. Okay? Okay, so let's stop.